want to take a minute here to go over the Unit 5 review, looking at some differential equations and some volume and area applications. I've already worked them out here, so just going to kind of give some quick commentary rather than a kind of a complete play-by-play, but let's take a look here. First problem here, we have a differential equation that represents the weight of a bird, and B is the weight, the current weight, and dB dt is the change of the weight with respect to time. First question is asking how fast it's gaining weight at different time, at different weights. All right. So when it's 40 grams, how is it changing weight? So changing here, if it's gaining or decreasing, that's rate of change. Rate of change is slope. Slope is the derivative. So we're just asking to find the derivative. Find the derivative when x is 40, and we get 12. Find the derivative when when capital B, when B is 70, and we get 6. All right? So which one's gaining faster? Well, this is a steeper slope. So when it's 40 grams in weight, then it is increasing weight faster because it's younger. And when it's older at 70 grams, then it's not gaining as much. That's the idea. So the second question here is asking about the second derivative. So find the second derivative in terms of b. That's the first question. Well, if we take our simplified version of that function, just distribute out the 1/5, then we get this thing right here. And if we take the derivative, we get 1/5. All right, it's negative 1/5, that is. It's a constant because the original function, or the slope function, is a linear function. So the second derivative is a constant, and it's negative. That means it's concave down. Negative second derivative means concave down, so it's always negative 1/2, so it's always concave down. Is this concave down? No, it's concave up and then concave down, so we get a problem there. It's got to always be concave down. Third question here, we want to use separation of variables. Now, separation of variables, this is the most important thing that we're working with right now, is we want to be able to find out what the function is, what b of t is, by integrating. But we can't integrate until we get dB and dt on separate sides. So we got to get all the b's on one side, all the t's on the other side. Notice there are no t's, so we're just going to divide to bring this over, multiply to bring dt over. We get this. If you want, you can make it 1 dt. Now we can integrate both sides here. And when we integrate, we got our dB, we got our dt, so we're integrating with respect to b here and with respect to t. And we're going to use some u substitution, so we're going to get a natural log here because b is in the denominator. And we'll get the negative because of the u substitution. Let u be 100 minus b. And we end up with, we'll need a c, so we get t plus c. You got to have a c on one side. Solving this for b, we're going to exponentiate. Get the 100 over there, all right? We're trying to get b here. So move the 100 to the b, and we get this guy, all right? So now we've got this function with a c. This is the general solution. We want the particular solution. Particular means what is c? We got to find out what c is, all right? So we need to know a t value and a b of t, and we were told that in the problem right here. We're told that b of t, or b of 0, is 20. So 0 is our t, and this is b of t, is 20. So plug in 20 for b of t, plug in 0 for this t in here. Simplify, we end up with c is negative 5, natural log of 80. Now we have that number, we can plug that in for c down in this general solution, and we end up with this. Not very pretty, but for the AP test, you don't need to simplify. We could probably mess with it, but we don't want to. All right, let's keep going. And another differential equation here. We got dy dx is e to the y times 3x squared minus 6y. Y is a function of x here. And we know it goes through 1, 0. So those are called initial conditions. That's going to help us find the particular solution. First one's asking us about a tangent line. Tangent line is going to have slope-intercept form. So when we see tangent line, we're thinking y equals mx plus b. We need a y value, and we'd like a b value if we can. So we got to find, we need a slope value. I said that wrong. We need a slope. Well, slope is dy dx. And we know that we were looking for the slope when f passes through 1, 0. So 1 is our x, and 0 is the y, of course. So we plug that into our differential equation. 0 for y, 1 for x, and we get -3. Now you can use point slope form here. Y minus y1 equals m minus times x minus x1. There's our x1 there. And we get our slope equation. Now, the idea is this. We have some graph. We don't know much about the graph, but we know it goes through the point 1, 0. So there's 1, 0. And it can be squiggling and curving and doing weird stuff like that. But we know that there is a tangent line. Anyone interested in helping out? Yeah, okay, that tangent line goes right through here. And it's close to, now my graph's pretty sloppy, but it almost is going to follow that graph for just a little bit. That's the idea. So we can use that tangent line to approximate the y value by plugging in that x value, 1.2 as it says. Plug in x 1.2 for x and see what y is. Well, on the line we get a y value of -0.6. That means that line's going to be right down here, and the curve's going to be close. You know, I put my curve right on it, but my curve's going to squiggle. It's going to be a little bit off. You know, this curve might, actually go like, okay, like that. So it actually separates a little bit, but it's close. So this is our approximation. That's the idea. All right. So now we can find the particular solution. So we need to do our separation of variables to get the particular solution. So we're going to move the x's, actually multiply by dx and divide by ey. That'll give us e to the negative y. Integrate and then solve for y. We're going to solve this for y, multiply by negatives. Now we're going to take the log of both sides. Okay, and then we'll multiply by this negative. It's going to give us that negative there. And that c that we got from integrating is going to end up inside the log. That's important. That's inside. And so we know that it's going through 1, 0. So now we can plug in 1 for x and 0 for y and use that to solve for c. Now we know what c is. So we had plus c here, so we're going to put -1 in. That is our particular solution. All right? Up here we had a slope of -3. At the point 1, 0. So at the point 1, 0, we've got a slope of -3, something like that, maybe a little bit steeper, but it's fairly steep. And then what happens is at each of these points, we need to plug in the coordinates like 1, -1. Well, when x is 1, this comes out to be -3, and then when this is -1, we get e to the -1. Well, that's like 1 over e, which is 1 over 2.7, and 1 over 2.7 times -3 gives us about -1. So this should have a slope of -1. Maybe not steep enough, but that's the idea. It's less steep than this. And this guy's going to be even less steep. And we're going to get more and more steep in the negative direction as we go this way. On the other side, we'll end up with a positive version of that. All right? When x is -1, this comes out to be 9, right? So it's 9, so it's very steep. So that's why this has a slope of 9. This has a slope of 9 times e. This is 9 times e squared, very steep. Okay? These all have x values of 0. They're all going to be horizontal because when x is 0, this goes away. And that makes the whole thing 0. That's the idea. All right, I think we got that. Quick look at some volume, all right? So volume here, we need to be able to graph our curve. You need to know that a log looks like this. Now, this is a calculator section. Lots of calculator going on here, all right? So you need to understand the concept, but let the calculator do the work. So if you need to graph this on your calculator, do that. We have an asymptote here. The area that we're talking about is bounded by x equals 3 and the x-axis. So there's our area. Okay? We want to find the area, so we need to subtract these two. The log minus the horizontal line of 0. You use your calculator, and you get 8 natural log of 2 minus 3, which actually we probably want a decimal value, so whatever that decimal is. Okay? If we want the volume, if we want to rotate this around the x-axis, so we're going to rotate this around the x-axis. This is going to be the disk method. Okay? So we're going to get these little disks going on here, all right? And so each of these disks will have a radius of the function itself. So we have pi r squared is the area of a circle. They're all circles. So pi times the function squared. Use a calculator. Don't try to take the integral of that. That's a mess. We don't know how to do that yet, so use your calculator. If we want to rotate around the line y equals 3, that's right here. Now we're going to rotate it this way. Since this is below y equals 3, it's going to be a washer. There's some space going on right here. Do you see that? So we got space. And so since there's space, that's what makes it a washer. So this thing's wrapping around. So washer method, we have to subtract the big radius minus the little radius. Well, the big radius here is this distance from the center, or the axis, I should say, the axis to, come on. Okay, that's big R. Little r is this function right there. Okay, actually little r might be better to see it as this. Okay, that's little r. So big R is always going to be 3 because it's the distance between this line and the horizontal axis. Little r in this case is going to be 3 minus the function. That's the distance between 3 and the function. And that's where we're getting this. Okay, so we have big R squared minus little r squared. And we use our calculator. Okay. The shell method here, this next one, sorry, we're going to rotate around the line x equals -1. Okay, so we have a couple ways to go. We can do the shell method, thinking about this. Shell method is like the surface area of a cylinder, 2 pi RH. So we have 2 pi. The radius of this cylinder is going to be whatever x value we pick minus -1. That's the radius there. The height of this, well, that's just the height of the function, natural log of x plus 1. And so we're all set up. Use a calculator to integrate, and you got it. Okay, all calculator. If you want to use the washer method, a little more challenging. We've got to solve this for y to use the washer method. And when we solve this for y, we get, solve it for x, I should say. It already is solved for y. This is x equals e to the y minus 1, because if we're using washer method, now we need to think of a disk going this way where this thing is getting spun around, making a washer. Okay, so we're talking about this horizontal. Okay, a little more challenging in this washer method here, but we end up with big R is going to be 3 minus -1, which is 4. Little r is something weird happened here. I think this E here is supposed to be down here. E to the y minus 1. That's the function minus -1. I don't know what that E, it ran away. Okay, and that's just the -1s are going to cancel there. And you have e to the y. Use your calculator, and we get 46.121. All right, last one of this group is we're going to put semicircles on this. Well, we're going to put these semicircles on this, these little semicircles going on here. They have a diameter. Their diameter is natural log of x plus 1. So the radius is half of that. That's where this is coming from. Area of a circle is 1/2 pi r squared, a semicircle that is. So now we're just going to integrate to add all those up. All right, we got 1/2 pi r squared, and there's our radius. And 2 squared times 2 is going to give us 1/8 pi. And we end up with the natural log, the function squared in the end, okay, which gives us 1.02. We are cruising through, getting the big ideas here. That's just what we're going for. I'll let you pause and think about things more. Next one here, we've got the sine of x and the graph y equals 1. So here's the sine of x. Here's y equals 1, and it's bounded by the y-axis. Real important that you identify and sketch for yourself what that area looks like. Now we're going to revolve it. Oh, first find the area. So we got 1 minus the sine of x, and we're integrating from 0 to pi over 2. So you got to find these 2 points where the functions match. Integrate that thing, we end up with 0.571. I did it by hand there, but this is calculator action, so use your calculator. To find the volume of the solid here, when we rotate around the x-axis, well, we're going to get this washer method when we spin this around the x-axis. Take one rectangle, spin it around, you're going to get a washer. The big radius is going to be 1. The little radius is going to be the sine of x. Okay, so we have 1 squared minus sine x squared. Okay, watch out for this. The washer method is big R squared minus a little r squared. And it's pi times that. Okay, so that's the idea. 2.467 there. Then we're going to find the solid, rotating it around the line x equals 2. So we're rotating it off to the right. This is probably best for shell method. You probably want to avoid washer on this. It gets weird. So shell method here, 2 pi r h is the area of the cylinder. So the radius of this cylinder is 2 minus whatever this x value. You pick an x value, or we're going to pick a whole bunch. Okay, and we have 2 minus x. Okay, that's the radius. The height of this is going to be 1 minus the sine of x. Okay, something's missing here. We have our bound 0 to pi over 2. Okay, and we end up with 5.704 there. You can use washer method, but it's just going to get ugly. Okay, because you got to solve it for y, and you just don't want to do that. Write the equations of the axis of the revolution. That could use a disk method. So the idea here is this. If we spin around this, we can use disk method. If we spin this way, right? If we get these little circles that way, we can use the disk method. If we spin around the line x equals 0, the axis, we can use it. We'll get disks, okay? So we're going to get this area in here, and disks would be great for that, okay? So 2 lines are x equals 0 and y equals 1. Last but not least, if we put rectangles on top of here whose height is 4 times the base, first thing we got to do is we got to define the base. The base is this length of this line, 1 minus sine x. And the area of a rectangle that we're going to stack on top of here, okay? If we can see this 3D rectangle, we're going to set on here, okay? We're going to stack a whole bunch on here. 4 times taller than they are wide. So the area of one of those rectangles is base times 4b. And so the base of that is 1 minus sine x, and then the height is going to be 4 times that. So it just ends up being 4 times the integral of 1 minus sine x squared. Okay, from 0 to pi over 2, and we got 1.425. Let's keep rolling. Here's an AP test question. This would be a no calculator. The reason why it's no calculator is because we're not actually going to evaluate this, just seeing if we understand the concept. So we've got our area given to us here. We've got our functions given to us, 2 square root of x and y equals 6. That bounds this. To find the area, let's do 6 minus the function. Okay, and this one we can evaluate. Pretty simple function, the square root of x. And we end up with 18 on that. If we're going to revolve this around the line y equals 7, so up here we have the line in y equals 7. Our area, our region only went up to 6 here, so this was just up at 6. And that's going to be a washer method, okay? And so you could use shell method as we show over here, but washer method, big R is going to be 7 minus the function. Oh, looks like I messed this up. Minus, what's going on here? So the big radius of this is going to be 7 minus the function. Oh, I'm going to hear about this one tomorrow. Volume is pi times 0 to 9, and we're going to have 7 minus 2 square root of x. squared. Okay? That's the big radius there, right? That is this radius for any particular washer going from 7 to the outside edge. The inside radius, well, that's going to just be 1 because that's this distance here from the 7 line to the 6 line. And that's 7 minus 6, which is 1. So I have minus 1 squared dx. Okay, so we'll see who is the first one to catch that tomorrow if you read the other solutions. This guy is just wrong. Okay, you got to have that 7 minus there. If we want to use a shell method, well, we got to solve this for x, which is not terribly hard. And then we have a shell. Here's my shell right here. And the height of that shell, well, first of all, the radius is going to be 7 minus the y value that we pick. We're picking the y value. And then we're going to compute this distance here, compute the x distance. So the y value that we're going to pick is going to be 7. Let's see if we did this one. All right, we did. 7 minus y, that's the radius. And the height would be this function. When you solve it for x, you get this function here. And that is going to give us the height. And so there's our other possible function. And the AP guys would be fine with either of those. All right, and so last but not least, we're going to put rectangles on this like we did before on the previous one. Area of the rectangle is b times 3b because this one's 3 times its height. The distance here is 6 minus the 2 squared of x. And so we have the integral from 0 to 9 of the base times 3 times the base. You could leave it like that. That would be fine. Or if you want to pull this 3 out and have 6 minus, oh, look what I did. Another typo. I don't know. I might blame that one on that might have gotten deleted by the program. Anyways, there it is. That's from 0 to 9. Okay? All right. Lots of stuff going on there. Hopefully we get those big ideas of disk method, shell method, washer method, all right? And when to use those. And then we also have these cross-section methods when we're stacking stuff on top. So keep working hard, and we'll see you for the test.